Namaskar, welcome back. So, in last lecture, we discussed about the significance of historical and modern seismicity, and we also discussed few examples from Europe, India, and in India, particularly from Kutch and Kashmir part, and as well as from the Kangra Valley. So, based on those informations, what we have in the historical chronicle as well as the ancient documents helped to some extent uh, to understand the hazard posed by that. We also looked at some archaeological sites from Indo-Gangetic Plain, that was the your Aichhatra near Bareilly. So further moving ahead, because those things were all related to the ground shaking, seismic shaking. Now we need to have an understanding of what exactly we understand about the or we know about the seismic waves, how they are generated, and how many types of seismic waves are there, and what sort of damage it can create. Okay, so that part is a bit important, and then slowly we will move to the evidence or the signatures which we should look for the ancient earthquakes or historic or prehistoric earthquakes preserved in the sediments and landforms. So that part we will do it later. So this topic basically gets related to your interior of earth, which we had a very brief discussion about the interior of earth when we were talking about we discussed about the plate tectonics part. Okay, because that was the beginning of uh, uh, the uh, the portion which is important to understand that how the plates are moving and all that. Okay, now here so in that lecture we also learned about the plate boundaries and all that, but here we will talk about that what are the different type of seismic waves which are generated during a sudden release of the stored energy, and that is your earthquake, and how it results into the or causes the damage to the areas in the epicentral area, away from the epicentral areas. Okay, so these are the few things, because if we keep talking about that, okay, fine, zone 5 is, for example, Himalaya is in zone 5, then we are not sitting away from that region, will not we will not get affected in terms of the damage, but it is not true actually. So coming to that, the interior of earth again, we understand well that it is not homogeneous, the interior of earth. It has different units or layers, we can say, depending on their physical properties as well as chemical uh, compositions. Okay, so we have broadly, if we divide the interior of earth, which goes right up to like more than 6,000 kilometers. Okay, that is the deep the interior of earth. It has mantle, and then you have the crust is on the top, then you have mantle, and then core. Okay, so if suppose we say that, okay, fine, the interior of earth is homogeneous, then any earthquake or the energy which has been released and the seismic waves has been generated will travel through and through, and they will not have any sort of a distortion, refraction or reflection. Okay, or they are not going to be reflected back, or they are not going to be refracted. Okay, so this is the diagram which it shows, but this condition is not true actually. Okay, so there are two type of seismic waves. One we call as a body wave, and the body wave is again been divided into P and S waves. That we will slowly will come to that part here. So this is the velocity equations of both the waves, and it you will understand that what why this based on the behavior of this waves and the way of propagation. Okay, so these equations have been generated, and where k is your bulk modulus and mu is your shear modulus of rigidities, you can say, and then the density. So it So property, based on the properties and all that, these waves will behave differently. Okay, they may travel faster, they may travel slower, they may die out, they may not be able to go through certain layers. Okay, and that what has been identified by measuring this seismic waves when they are generated, and by the instruments which they record this type of seismic waves. Okay, so if you look at the uppermost part of uh, the earth, okay, then you go deeper. Okay, that is what I was talking about, that if you go until like 6,000 kilometers below, and we are having like the crust, which we also call lithosphere, then we are having a asthenosphere, then you have the mantle part and the outer core. Okay, so this also falls the below the crust, it falls into the mantle part. Now, yeah, if you look at the propagation, or we can say the velocity of the seismic waves which are generated. So first, if we take just the body waves and then we say that P and S wave, both are not behaving in the same way in terms of the velocity. Okay, the velocity changes as you move, as it moves through different units. The velocity changes, and one of the wave from this, that is your S wave, uh, do not travel through the outer core. It dies out there, and the reason there is that you won't be able to share, because this is the property of this wave, or characteristics of this wave is the sharing characteristics. So it will not be the particles which are moving, or we can say the waves which are propagating in that direction with this sharing component will not be able to share itself in the liquid outer core, and that is one of the reason it dies out actually. So it doesn't go further. Similarly, if you look at this is what we call the low velocity zone, and this low velocity zone is your asthenosphere next to your crust. And this we have already discussed that this asthenosphere, which is a low velocity zone region, is partially molten. It is not completely solid as crust. Okay, and all crust or the lithospheric plates are floating on this, and hence they are also moving on top of this. Okay, so if you look at we will come to the details of the velocity and all that, that what is the velocity of the P wave and the S wave and all that. But if you carefully look here, then what you see is that it definitely increases, the velocity increases in the crust here, it starts. Okay, and then it reduces in the uh, low velocity zone, which has been shown here. Okay, so it reduces and then further it gains up. Okay, but P wave goes through the liquid, it gets diffracted, its velocity slows down and all that, but it goes through because of its property. And this is very much similar to your sound waves. Okay, so it compress and pull, so push push pull push pull, nature is there. So let us see further what we have. So this is your uh, P wave, which of course, as it comes into contact with, or the contact between the mantle and the core, outer core is liquid, it slows down respect like drastically, and then further slowly it gains the velocity and goes through the inner core also, whereas the S wave doesn't travel through that, and that is one of the reason is that it has a shearing component. Okay, so seismic waves further, if we try to categorize, then other than the body waves, we have also surface waves, which mostly remains along or travels along the surface of the crust. Okay, of course, it travels little deeper, but not as the body waves. Okay, and they are termed as the love waves and the surface relay waves. Okay, these are most damaging one because they mostly confined and travel along within the top surface, and they are developed at the later stage also. Okay. Now P waves, if we take, as I told, that it is also termed as the compressive wave. Okay, so compression is there, and as you see here, the video of if you hold a spring and then push you stretch it and leave it, then it results into the push and pull. Okay, so that propagation of this is typical of what we say that is a compressional wave, and as I told, that it is very much similar to your uh, sound waves. Okay, so motion is in the same direction as the direction of the wave propagation. Okay, it is one of the fastest wave, arrives first. So when the earthquake has been triggered, and when it is measured by the seismometers and all that, it will arrive first because the velocity is higher or highest, we can say. So the speed or the velocity is around 6 to 6.5. This is in crust actually. So kilometer per second, 6 to 6.5 kilometer per second. It pushes and pulls the ground. Okay, as we can see here, okay, it pushes and pulls the ground. Produces sound, motion similar to sound waves. Okay, so whenever there is an earthquake or the sudden release of your energy stored in the crust, okay, and that processes your earthquake. So whenever there is an earthquake, you will hear a sound in the nearby area, or you can say in the epicentral area. Okay, can propagate through solid, liquid, and gas medium. Okay, so the medium of the Earth's interior, it plays a very important role. Okay. Now further, so this you can just remember that this is a compressional wave and also termed as your primary waves. Now coming to the another one, that is S wave, is a secondary wave. Okay, and here the direction of propagation is also like it is perpendicular to the direction of wave propagation. Motion is there, and it results into up and down. Okay, it moves the land up and down. So first one was push and pull. We have this wave is it will result into the waved up nature of the ground. It moves like that. Okay, so it arrives first. The velocity is almost half, 3 to 3.5 kilometer per second. Okay, so moves ground up and down, can propagate only through solid. So this is the important characteristics of this wave. It is also termed as transverse wave because of its motion is perpendicular to the direction of propagation. It's also termed as shear waves. Okay, or secondary wave. That one, the P wave was primary wave. This is secondary wave, shear wave, or transverse wave, we can say. Okay. So now we have two part, like in terms of the direction of propagation. One was in the direction of the same direction of the motion, whereas here the motion is perpendicular to the direction of wave propagation. Okay. So the first sketch where we were looking at that if the earthquake is been triggered here and the earth interior is homogeneous, then we should all see the waves traveling through and through without any deviation or reflection or refraction. Okay, but since we understand now that the interior of earth is not homogeneous, it is heterogeneous, and that will result into some sort of a deviation or diffraction of your waves, which are capable of traveling through different mediums. Okay, so only we have the P waves which can travel through solid, liquid, and gas. Okay, but S wave doesn't, and that is one of the reason why you will not be able to receive, if your stations are sitting here, then you will not be able to receive the S waves. Okay, in this run. Okay, so this portion is what we call is all arrival of your P waves. Okay, and that is what we call the refracted P waves will be received by the stations which are sitting here, if we consider that there isn't the earthquake was been triggered exactly at the north point. Okay, so that's what we are taking into 0. Okay, and then this complete goes up to 360 and all that. Okay. Now, so this portion, if we divide the overall globe and then see, then this is your 90, okay, and this is your 180, what you are looking at. So in this region, you will not be able to receive any uh, S waves. Okay, and uh, this portion, if you look at, like, this is a shadow zone, that what, yes, okay, one more point, important point is that we, wherever we are not able to receive a particular wave, then we seismic waves, then we term that area as an shadow zone. So this one is that because it is getting diffracted over here or refracted, and then it is traveling through this and received here. Okay, so based on that, this portion from 103 or 104 and 143 degrees, you will not, no direct arrival of P waves will be there. Okay, no direct arrival because they are getting uh, refracted. Few will be just, we can see that they are deviated and they will be received over here, but the few which travels through this will not be seen here. Okay, because they will not be seen in this region, that is 103 to or 143. Similarly, this is a shadow zone which marks no direct arrival of S waves because they are absolutely not able to travel through this region. Okay, so they are not traveling through that. So they will just get they are having the outer core, they cannot travel, so they will just are diffracted over here. Okay, so between 103 to almost 180, we can say that is the your S wave shadow zone, and this one is your P wave shadow zone. Now, this is again the same figure which we were looking at there, that shows the that the P wave and the S wave. So P wave cannot reach the surface within the shadow zone. That means in this area, it will not able to read because of way the way they are refracted when they enter and leave the core. So when they enter the core and leave the core, they will not be able to, we will not be able to receive in this region. So degrees are like in some text it is 143 or 142. That doesn't matter, okay, much, but we will fix up that which mainly the portion we should consider for this. Okay. Now S is like S wave reaches the core, they cannot travel through its liquid outer core, okay, or outer region, and therefore never emerge beyond 105, okay, from the focus. So this is the focus, we can say the 0. Okay. So the waves where have been earthquake was triggered there, and then we have the waves which are generated. So we will not be able to see others or record the S wave in this region. Okay, that's what we have discussed in the previous slide also. So finally, if we look at the P waves, it looks something like this. It can travel, so it will be received over here, it will be received in this area, and this area. Okay. Whereas the S wave only in this portion. So you can take, like we were talking about 142 and 105, but you can just take that. Okay, both are correct, no issue of that. Okay. So 103 to 143 is the P wave shadow zone, and that is between this. Okay, so this is P wave shadow zone, and from 103 to 180, okay, till here. So we have like no S waves are been received in that area. Okay. Now, if you consider that the earthquake has been triggered somewhere at almost like 270 degrees somewhere here, okay, and this was the focus, okay. Now, if this is the focus, then what we are expecting based on what we have seen in the previous two slides, okay. So, magenta color is showing your S waves and blue one is the P waves, okay. And this are all stations, okay. So, these are all stations which are been installed, or and so what will happen is that, as we have learned, that this is either 103 or 105 if we take, okay. For example, this is, but it will change as with respect to your focus, because now this is 270, but that difference will always be seen, more or less will be seen in terms of what we were looking at in the, if the focus was here actually, okay. Now, if you look at this, then if the stations or the people who are going to be on that particular area will be experiencing both the waves, that is your, this region will experience all both, because P and S waves are been received here. But in the shadow zone, again you will have that there is no arrival of the S waves, as we have discussed there, and then in this region you will not have, you will not see the arrival of the P wave, okay. Now, there were like seismologists, they keep on working on this, and they have also identified that there are few waves how they can classify, and then they are having like the classification of these waves, which are like, for example, here the PKP, okay. If you see, then that wave is transmitted through liquid outer core, and PKIKP is this one, okay. So, it is the P wave, and then you are having core, inner core, and then you are receiving the peak wave basically. So, they have the different classifications which have been done, but more or less what the take home lesson is that the P and S wave doesn't behave in the same way, okay. The P waves will travel through even after having refracted, and then travel through outer core, liquid outer core and the inner core, but the S waves will not be able to travel through that, okay. So, P and S wave and surface wave paths from focus to seismogram, okay. So, this is how one will be interested and will be able to measure the seismic waves, okay. We'll come to this part about that, what are this uh, seismograms are able to tell us, and the curves, we'll talk about that. This helps in identifying the epicenters also, okay. Now, S wave if you take, then you have uh, again that what we are having, the shear waves, these are the shear wave or secondary waves. P wave will not result into much of the damage, because it is just producing the sound and also push and pull the ground, okay. But S wave will move the ground up and down. So, you expect some damage from this, okay, from the S wave, as it has been shown here that it pushes and pulls the ground, or you can, and in S wave it waves up the ground like up and down, okay, and the direction of motion is as shown by this arrow. Now, it is almost like perpendicular to that, because it is moving up and down, and the propagation is like that, so almost perpendicular. Now, can we see this type of examples on surface? And this is the best example which is available. Not only this, there are many more which have come up, that this is typical of the S wave which has traveled, okay, through this area. So, if you look at this part here, this is something like this. It goes this base of the floor and then goes up, okay. And even if you see this one, so this is typical of the damage related to your S wave, okay. And this is from 1999 Taiwan Chichi earthquake, okay. So we'll stop here. We'll see more examples of this and then try to understand about the behavior of the seismic wave and how like extensive the damage could be related to such uh, uh, seismic wave traveling through the crust. Okay, so I'll stop here. Thank you so much. Namaskar.